Thank you for joining us for Inspection of Large, Dense, or Complex Parts with High Energy CT webinar. My name is Nayara del Puerto, and I'm the marketing leader for radiography systems within Waygate Technologies. Before we start, let me cover a few housekeeping items. At the bottom of your screen are multiple application engagement tools you can use. All the engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can make a request to book a meeting or a demo directly from your console. You just need to click on the appropriate engagement tool and add your information. The slide area can be maximized to full screen by clicking on the arrows in the top right corner. If you have any questions during the webinar, you can submit them through the Q&A engagement tool at any time throughout the presentation. We will try to answer this during our Q&A session, but if a fuller answer is needed or we run out of time, it will be answered later via email. Please know we do capture all questions. We would also like to ask you to take a few minutes to please complete our survey. This will help us bring more topics and improve our future webinars. A copy of today's slide deck and additional help materials are available in the Related Content Engagement tool, and we encourage you to download any resource or links that you may find useful. So let me now announce today's speakers and their titles. We will have Shana Telesz, who is the High Energy Catalyst, and we will also have Tyler Ripperger, Application Engineer within Waygate. So all set, Shana and Tyler, it's all yours now.
Hey guys, thank you everybody for joining, and thanks for those of you who tried to join the one in December when we had some technical difficulties. Thank you for sort of sticking with us to kind of hear this presentation. You know, I'm going to go through a little bit about high energy CT. You know, I see a lot of different representation kind of on this call currently. There's a lot of industry challenges. I know I've talked to a lot of you guys personally, kind of go through, you know, what some of those are, how, you know, high energy CT can kind of help us, you know, what some of the typical target applications that we've seen success with, and then a little bit about the specific system that we have now built here in Cincinnati, and then kind of give you guys a couple conclusions and then questions, and then you guys can kind of feel free. All right, in terms of industry challenges, so I know talking to a lot of you guys, you know, especially in the NDE world, we feel this pain, right? Every day there's constant developments in manufacturing technology, you know, the new additives, the new multi-core castings, EV motors, larger batteries, etc. Keep pushing the envelope on technology and sort of what's available. Keep pushing on what's available and or what we need to do from an inspection technologies perspective. And you know, that bar keeps moving and moving. Parts keep getting denser, they keep getting larger, they keep using new materials, etc. So we need to just kind of keep moving forward. And with that kind of being said, I guess I want to throw it out there to you guys for a second and ask kind of a polling question of you know, how often do you guys experience limitations with your current CT technology due to lack of energy? How often are you facing this problem? I'll give you kind of a minute to respond to that. Right. Let's take a look at the results. All right, so regularly. So a lot of you guys are seeing this problem on a regular basis, and it's something that you deal with frequently. I think that that's kind of what we're seeing, is that a lot of people are starting to really come into this, seeing it frequently, or it's becoming a problem, right? So just to kind of maybe articulate that problem a little bit for those of you who haven't seen it yet, you know, this is an example of an additive component that, with current technology, 450 kV scan, you can see on the left side that there is significant lack of penetration. The scatter on the internal features is really not good enough, right, for us to do what we need to do. We've tried it with, scatter improving technologies, including our own scatter correct. And you can tell that the internal data is sort of improved and we're able to kind of reduce the scatter, but you still have lack of penetration in certain areas for key features. And early on, we kind of figured out, hey, if you scan this on with high energy, and a lot of high energy systems that are out there are with LDAs, right, that make it kind of a slow scanning process, building that line by line. So you're able to achieve the image quality that you need. However, the time, if you see, it goes to 13 hours, and obviously we need to be better, kind of as an industry to enable these components to meet production needs. Give you just kind of a couple other examples. We went and rated our shelves of uninspectable components. Here's kind of an aerospace component, made of, it's an Inconel component, it requires NDE and sort of metrology analysis on it. We scanned it kind of on 450, what's possible. You can tell that there's kind of a lack of penetration. There's artifacts, there's beam hardening artifacts, there's rough surface finish due to kind of the scatter. Really isn't good enough, right, with the current technology. Here's another component that's an additive component. This component, the top part of it is sort of able to be scanned with 450 kV. But that bottom part, that really thick, dense metal at the bottom is really not able to be sort of penetrated today. Here's another component. This is an industrial gas turbine blade. Another kind of example of not getting enough penetration with 450 kV, another kind of, application that's on the edge and not able to be inspected as those parts get more complex and require, more CT scanning. So now I'm going to show you a couple of examples of we took those same parts and kind of did an initial study on what could be done with high energy. So you can see this first component, kind of from the case study. Again, this is kind of a nickel-based alloy aerospace component. The original scan time with 450 was about 2 hours, but again, we saw the artifacts in the last kind of round of images. We took the same component and we scanned it with, 9 MeV to kind of see what was possible. And in just an hour, we were able to get uniform contrast of the entire part. We were able to get clear detection between the thin walls, and then, able to get a clear surface model to be able to use for dimensional analysis and metrology. So you're, again, starting to see kind of the difference in a part, and I think this is a vein segment. Okay, here's that other component that I showed earlier. Again, kind of the top area with the scatter correct in the 450, you were getting close to sort of good enough, kind of with the 9 MeV, and then kind of taking it a step further with 9 MeV with scatter correct, you're starting to see a much cleaner data set that you're able to do dimensional analysis on this component as well. This, again, is another additive component. Cobalt chromium requires both NDE and dimensional. Here's another, the case study with that industrial gas turbine blade. On the left, again, you're seeing the 450 kV images. A lot of lack of penetration, not seeing, the clear wall thickness or the clear features. And then on the right, kind of that same component with the 9 MeV. So starting to be able to get into these components, really see what the intent is. Here's another one. This is the part that I kind of showed you at the beginning to start with. Current state of this component is something like five scans or 5 different views, which are about 8 hours of scanning on a 450 system, and then moving it over to an LDA system that's 9 MeV, that's about 15 hours. So this one component has about 23 hours of total scan time to get it validated properly. You know, kind of our initial results from doing the validation and working through the validation of getting an official sort of approved technique for this part, you know, look like we're going to end up somewhere around 3 hours. And that's just in scan time. You know, I put a little note here, right? Obviously, if you're not looking at that many data sets, your evaluation time is also greatly reduced. So those are kind of some examples as to the why. I think I've got a couple more talking about the metrology. You know, a lot of these components that we're seeing, and a lot of you guys out there I know are also doing additive. You know, we're seeing first that we do an NDE, you know, scan, we do an NDE analysis, then we apply a bunch of noise reducing filters, and then we do the STL to do the metrology inspection. So again, this part, right, has a much better surface capability or characteristics. I showed that sort of earlier. Here's kind of another example of that, the difference between, you know, 9 MeV and 9 MeV with scattered correct, and the ability to kind of look at those surfaces and do the analysis on those surfaces. All right, with that being kind of, that went backwards there. Going to kind of ask you guys, throw another question out there. So what kind of components are you guys typically struggling with? Are they casting components? Are most people seeing 3D printed parts, composites, others, or I guess you're just not seeing them at all maybe? Give you kind of a minute to answer that. All right, let's look at the results. All right, so most people are seeing cast components and 3D printed parts, which is good because those are the examples I mostly showed you. We're going to talk about through some of these applications and through some of the other ones, and kind of, again, what we're seeing on those applications. So target applications, you know, the original, I think, sort of thought behind this whole journey was that we need something to address complex, high-density metal components, which is what you guys just said also. You know, the materials like the nickel-based alloys, the inconels, the steels, things looking at cumulative wall thicknesses of, you know, somewhere around 15 centimeters or 6 inches, you know, maybe even a little bit more. You know, people are asking us, right, to see porosity, inclusions, voids, cracks. With the additive pieces, you know, lack of fusion, trapped powder, surface flaws. And then on top of it, right, then we've got the added fun of the geometrical features, especially the internal features. There's a lot going on in these parts, especially on the additive and the multi-core casting side, right? There's a lot more design freedoms that allow for a way more complex shape. And then also, you know, these kind of these assemblies, you know, things kind of going together. You know, some specific examples of this, you know, there's a lot of heat exchanger kind of components, right? They are very nice, you know, for additive, a lot of structural and booster components kind of in the space industry, and even some larger car assemblies and truck sort of components. So these are the typical, you know, things that might be attractive to consider high energy for. And then, you know, as you kind of go down the density chain, if you will, you know, the large complex light metals as well. You know, when you get into really large, you know, titanium, aluminum, magnesium, zinc, you know, big, dense, you know, thick wall kind of components, you know, we need to have capabilities to go somewhere up to, you know, 12 inches of cumulative wall thickness or 30 centimeters. A lot of the same types of defects that we talked about with the dense metals, just, you know, these parts tend to be, you know, larger because they're lighter metal, but still require this kind of inspection. You know, just to go into a little bit with additive and the complex castings, which is also how a lot of you guys answered that question. You know, 3D printing, again, kind of allows for greater design freedom. So a lot of these components are really complex inside as they're, you know, consolidating multiple components, from a previous life. You also have the trap powder, which you can kind of see these images in the top right corner are, trap powder applications. Needing to validate, and you can see this in the bottom image, validating the sort of as designed versus the as built condition. Did we make what we thought we were going to make? And then the multi-core castings, I know some of you are pretty familiar with those, but looking at, stuff that was previously done wall thickness measurements with ultrasound, and doing them now with CT, and you can get through those multi-walls, look at the wall integrity, the wall thickness, et cetera. And finally, the last one, I think, which sometimes people don't think about as needing, more energy, more material, but these large composites, there's a lot going on with innovations on the composite technologies, going to CMCs, RTMs, make bigger components, looking for smaller characteristics. So even these components that may have cumulative thicknesses, the root of things like span blades, 18 inches, looking at sort of porosity inclusion, ply structure layers, wrinkles, delamination, needing to kind of look at these types of parts. These are also things that may be good fit, for high energy band blades, vanes, shrouds, etc. And again, kind of some examples of what some of these large composites, again, all these new manufacturing processes coming. They're very complex. We're creating defects we haven't seen before, and sort of taking a look at those. Now I'm going to talk a little bit about specifically, our high energy strategy and our high energy journey. A lot of you I know I've talked to over the course of the last year, but we basically went on this journey to, design and build a high energy system here and install it in Cincinnati at our CSC. I know a lot of you guys have been here before, but we basically put an entire addition on, a 7,800 square foot addition onto the 20,000 that we already had, and built this high energy bunker. It's roughly 2.5 million pounds of concrete. It has like over 80 tons of granite manipulator, and again, the 9 MeV and the 450 kV source. But we really looked to use our scatter correct technology and some of our core technologies from our other products to help, bring access and availability to the industry to this type of technology and work on getting scan times for these components down to acceptable production levels. So again, our system that we built here for ourselves, that's available for services, and then also, we're interested in helping people build their own as well. It has a 9 MeV Linac. It's got a Titan 450 kV source. As you notice, some of those parts in the beginning, sometimes they have thicker sections and thinner sections. So being able to do 450 kV and 90 MeV in the same system on the same mechanical scale will allow us to better blend that data and use the optimal, imaging chain configuration regardless of what the part looks like or the section of the part that we're scanning. We have dual detector, so an LDA and a DDA. There's an integrated crane in there. Again, we used our scatter correct. We used, our Datos X software, large part scanning capabilities, so the V sensor, the offset scanning, those technologies. And then also, we've built this thing with precision in mind to be able to do a level of metrology for these components as well. The part envelope, again, that we sort of targeted to kind of hit the middle of a lot of what you guys are seeing is roughly 2 meters cubed, weight up to 1,000 kilograms. And again, we just talked through sort of the defect types and stuff that we're hoping to let people see. you know, in terms of what we're sort of offering, again, the Cincinnati unit here is up and running. You know, we've started booking capacity for people who, you know, think they need this service or they need to investigate this technology or look at it. You know, if that's interesting for you, please get in contact with us afterwards, because as you guys know, this technology is not readily available across the world, and it does, we are seeing a lot of interest filling up fast. You know, again, we're interested to share our journey with other people, so if, you know, people have the need to have their own one of these systems and have it on site, we will certainly share everything we've learned along the way, the good and the bad and the ugly, and help you sort of build your own as well. All right, I'm going to skip to another polling question to make sure you guys are all still awake. How much volume do your different organizations see for high energy CT? You know, do you have enough that you already need your own capability? You could purchase some services, regular services kind of needed, or just a few here and there, or you don't really need it at all, but you're curious. We'll give you a minute. All right, wow, we're bipolar here. Okay, so we either people have enough interest already that they need their own capability, or not applicable yet. This is really interesting. Curious to see how we can help you guys through that. All right, a little bit more details on the specifics of this product that we sort of built. Again, I think I went through kind of most of this at a high level: 2 meters cubed, 1,000 kilograms in weight, dual detector, dual source. You kind of start to see the structure of it here. You know, the manipulator specifications, I'm not expecting you to read any of these, but I think some of the key highlights is we built the system incredibly flexible. We can have a source to detector distance all the way from 5 meters to 1.5 meters. 1.5 meters, you know, to kind of get in tighter on smaller components, but also, you know, go wide and get that whole 2 meters of sort of scan area. You know, we have actually the source axis is the one that is sort of moving closer. We've stabilized the detector axes, as there's a lot of weight there with the detector shielding, you know, needed to protect it, and then the scatter grid kind of on top of that. So we have chose to move our source and our component rather than the detector axes. But I think those are some of sort of the key aspects of the design. I think the other thing that's sort of critical is the back behind the detector is also open to also reduce the scatter coming from the manipulator itself and or the wall. Right, from an imaging chain perspective, you know, we use, for those of you that are already using our products, you'll be able to walk up to this system and pretty much use it as is. We're using Datos from an acquisition perspective, or reconstruction, a visualization, the data management. They're all part of our current product portfolio. We wanted this to kind of fit in. We wanted this to continue to be on the engineering development chain. Any new feature we develop should be applicable to this system as well. We've got, again, 2 detectors in this. We've got a flat panel detector. We used the Varex 1621. We've got 4x detector shift, and scatter correct capabilities are up to it on this system. The detector can basically move to 4 positions across. We've got the LDA, which will be installed here shortly. And you can see we've used one from Detection Technology. And then we've got a linear accelerator, and we decided to choose a 9 MeV with dual focal spot. So less than 1 millimeter focal spot and then less than 1.5. So we decided to, you know, for a lot of the components that we wanted to see, that the focal spot was going to be one of the limiting factors in our ability to achieve resolution for a lot of these additive components. So we went this direction. And then again, there's a 450 kV source in there, which, as I sort of described and mentioned, is really for the sole purpose of being able to, mesh different data sets and use, the optimal energy for each section of the component. Again, the room that we sort of built for ourselves, or the room required to house what we made for ourselves, you can kind of get a feel for the dimensions here. It's, approximately, 36 feet high, 18 feet in length, and about 19 in width. So it's a pretty big system here. Again, we've used all of our normal components, all of our normal proven technologies. We wanted this to be something that is sustainable, maintainable. We wanted it to not be something that goes away in a few years or becomes unsupported. We want it to be a core part of our existing product line and use the key innovations that we use in all the parts of our portfolio. So I want to go through a little bit of this real quick just so you guys understand, for those of you not familiar with our products. On the Datos acquisition side, this is our standard acquisition software on all of our CT systems. It allows for scripting and sort of automated data acquisition. It's got all of our, typical features, the multi-scan, the beam hardening corrections, scan optimizer, etc. You can utilize all the same features that you sort of use today in your conventional stuff on the system as well. On the reconstruction and analysis, again, you've got kind of all those same features that we have there. Looking, across the DiCondi export, the GPUs, multi-volume reconstruction is all available in this product as well. Our scatter crack technology, for those of you who know our products or know what we do, I think this is a big deal for the industry and a big deal for this product specifically because of the size that these pieces tend to be. Again, for you guys that aren't familiar with this technology, we basically, typically you get better scatter properties with an LDA as you're only capturing the X-rays that are going, straight through. With a scatter correct technology, we're able to use an area detector. So in this case, the active area ends up being about 13 by 13 after it gets shielded. We're able to take an image or images of the parts, 13 by 13 inches at a time, versus a 0.5 millimeter or 1 millimeter, at a time, which allows for some of the significant savings in scan time that we sort of talked about at the beginning. Again, kind of an example of kind of the results. So, with scatter artifacts, without scatter artifacts, being able to get better results, especially from a metrology or surface determination perspective. And again, the benefits of kind of this technology, right? You kind of get the best of both worlds, if you will, of getting reduced scatter, but you get the time of an area detector in terms of scan time. You also have access with the system to our offset CT scans. So this, again, you can kind of scan larger objects with offset to enable that. The Ruby plate, which is one of our phantoms that allows for sort of faster calibration and verification. The same phantoms that kind of work in our other systems are useful here as well in terms of doing, the same system checks that we see across the industry and the industry standards. And then, again, the 450 kV source is our normal, Titan Neo, easy to kind of maintain, quick disconnect connectors. you know, sort of proven capability, although I think we're going to prove it in a completely different way as it's now installed in a high energy cell. You know, we take advantage of our InspectionWorks product line as well, our software solutions, so integrating kind of that whole archive scenario, you know, dealing with the whole data management structure. The system works as well with that to, you know, help either pass data back and forth, help maintain and store, help, you know, set up workflow rules of how long, you know, a certain set of data has to be set, whether it's for 7 years or the life of the asset. This Rhythm Archive product feeds into this as well. All right, that's what I have in the main set, and we're going to start, Tyler's going to start looking at the questions here in a minute, but while we're doing that, just kind of show you a couple things. So this is kind of a lot of this while this thing was in process. This was the base stone for the manipulator. You can kind of see it had to get directly cut out of a quarry somewhere in the world, and was there. This is when the new building was being constructed. A significant foundation had to be laid, you know, to be able to support the weight of this machine at the end. You know, built the whole building. Well, meanwhile, sort of on the other side of the world, you know, the manipulator was starting to get built up and the granite put together. This, you can start to get a sense of the scale of, you know, a human versus the size of this system. And, you know, somebody sort of standing on it, you know, the bunker starting to sort of go in, you know, and finally we ended up with a new building with, you know, a 80 tons of granite manipulator inside a 2.5 million pounds of concrete bunker is sort of where we ended up. And it actually looks prettier now because they just finished the outside cladding, but this is kind of what it looks like at the end of the day. So I'm going to switch over. We're going to take a look at some of the questions.
All right, so one question we have is X offset scanning available on the 9MeV? Yes, that is correct, it is. So with this technology, we're able to offset the part in the X direction to achieve larger diameter components. So we can do this. On the 9MeV, this system also has deep sensor capability, so able to increase the detectors 3 times the limit with scatter correction. What detector is used? What DDA detector is used? Shana, do you want to take that one?
Yeah, we actually, in this case, we did not use our Dynamic 41 in the first version of this system. We actually chose to use to kind of take the variables out of the equation, and we used the Verex XRD 1621 for its sort of proven high energy capabilities and folded out electronics for this system, and it has the speed that was needed to do the CT scanning that we wanted to. So we chose that one at the time being for this, and that's actually something that we'll sort of continue to evaluate if we want to do something special there, or if that detector serves the needs of the applications.
How do you verify porosity testing accuracy within CT? There's a couple ways to do this. Typically what we see is we will scan a part with known defects, a part that has porosity, and then the company that is asking us to perform the scan will destructively test or destructively cut up this part and kind of validate our CT images to what they have from the cut up. And that way we can kind of validate the size and then also look and see what we are seeing or what we're missing within our CT scan.
Yep. And then I can answer the question about there's a question about what is the source to detector distance and is this changeable? The answer is yes. So the scatter grid that we've developed for our initial system, the one that we have installed now, is for 2.5 meters source to detector distance, but the system itself can go from about 1.5 meters all the way to 5 meter source to detector distance. So there's quite a range there.
So how do you validate image quality versus the requirements? Very common question that we see day to day, and especially with some of these larger additive or larger casting parts that we're seeing within the facility. And what we like to do is create an RQI, or a representative quality indicator of the part, with known defects within the part. So if the drawing requirements or the manufacturing requirements are to see a 15 or 20 thou defect, we like to put these indication types throughout the part in areas where we're having trouble with penetration, areas that we're having trouble with beam hardening artifacts, to kind of validate if we have full 100% CT coverage of this part. And using an RQI is definitely a way to achieve this.
I'm going to do something funny right now, and Tyler's probably going to swear at me here in a second. Hopefully not. Hopefully not with all of you guys listening. But somebody asked a question about what roughly is the resolution, and I think we should address this, even though the answer is depends.
Yeah. I mean, it really depends on the part size, the material that we're trying to achieve or trying to scan. I think we're fairly confident that we can get down to a 15 thou defect. It's really going to depend on the size of the part, the material that we're scanning, and what our geomag will be for this component. But we feel pretty confident with the scans that we've done on different RQIs, Inconel, cobalt chrome, that we can see a 15 thou indication.
Yep. There's a couple questions related to sort of the cost, and this is kind of another loaded it depends sort of question. I'll be incredibly transparent kind of with our own situation here. We had to build a building, we had to put in a foundation, we had to put in, a bunker, and then, the CT system kind of on top of it. And I would say in total for us, that ended up being something like a $7 to $8 million kind of investment by the time we, did all that. But I think the answer for everybody depends, right? What do you already have? What does your building already look like? What does the foundation look like? We were lucky that our foundation here at this facility is built on solid bedrock, so we didn't have to, deal with pylons and things like that. So the answer is it depends. I think on a case-by-case basis, I'm happy to help you, work with you, share anything that we sort of learned along the way. I would say the bunker itself ranges from, $1 million to $1.5 million. The CT equipment for the size and the capabilities that we've installed with the features, maybe something like 3.5 to 4.5, depending on sort of what you choose, million. So it really depends, and this is something that, it's a project, and we'll have to work with, you and your facilities, should you guys kind of decide to go under that. We've obviously, like I said, learned a lot on the way. For an actual system, that's kind of how it costs. I see that there's also some questions in here about, is the system available for rent and the service, and, what are kind of the costs of the services? Yes, the short answer is yes, it's kind of available, to scan your parts, or for you to come in and kind of use it with us for a while, or do it, especially kind of as, this is kind of, I guess another option available in the industry with this type of capabilities, to you guys. Yeah, feel free to contact us. We can definitely talk about that, and then, we can work up some sort of price for rent based on your scope of work, and what you guys would like to achieve. But it is definitely available. We encourage you to let us know sooner rather than later, because filling up pretty quickly, and I need to justify to our leadership, that we need a second one to help you guys out. So there's the answer to that question.
Okay. Is there a set voxel size for this system, or is it variable? This will depend on your geomag, the magnification that you're at. You're able to adjust the voxel size. So we have a 200 micron detector. Our vocal spot on the Linac is 0.75 millimeters and 1.5. So we have two different vocal spot sizes, but the geomag will affect the voxel size.
I think this is a good question. There's a question about why did we go straight to 9 MeV? There were obviously a lot of options between 450 and 9 MeV, and why did we sort of go that route? Honestly, we did a lot of research kind of in the 600 kV range, because obviously that's the shorter putt to move from 450 to 600 and not get into this whole bunker and this gigantic investment. But we found really with the dense metals and a lot of the parts that we investigated, it was only buying us something like a 1/4 inch to a 1/2 inch of extra penetration. And the problems and the challenges that we were seeing from you guys were, much more significant than that. We needed inches, not fractions of inches. So we kind of quickly rolled out the 600 kV. We also did a lot of homework and talked to a lot of people that were in the industry that had these systems. There's a few people who were super innovators 25, 30 years ago, and have had this. And as we visited them, a lot of them kind of made the statements that, hey, we have a 6 and, the ability to switch between 6 and 9 MeV, but we really always use it at 9. We kind of always run at max power. So we talked a little bit then, to Verax, who's the manufacturer of this, and, they gave us this option for the dual focal spot, and, I think we're the first ones that kind of have this option of the dual focal spot. And again, Tyler mentioned our small spot is 0.75, which is phenomenal, and I think we're really seeing a difference in the results because of that, and being able to, not deal with the effects of geometric magnification as much. That was kind of why we made the decision that we made for our applications. Is there anything else in there?
Yeah, I mean, as far as industry, these are questions around industry. I mean, obviously, space and aerospace are two really, common industries that we're seeing high energy in, but we are starting to get some batteries, larger batteries, on the system. So we're open to scanning anything that's, you've had trouble penetrating before on a 450 kV to kind of help you guys out.
There's some questions about dimensional accuracy. To be honest, I think some of this for us is a little bit to be determined, and again, kind of dependent on the part. But we're finding maybe address the repeatability of the system is really accurate. We use very high precision rails and motors. The whole thing is granite. So we're seeing a very high repeatability and, an ability to get to the exact location and stuff that we want. So as we continue to validate this and work with parts, we expect, the metrology capabilities of this system to be very repeatable and very accurate. The question about secondary radiation in detail, does it produce secondary radiation, or does it make kind of the components radioactive? Not really at 9 MeV. We did, for safety reasons, put an ozone sensor, in our system to kind of measure that, make sure it's safe before we open the door. But so far that hasn't gone off. I think once you get above 9 MeV, you start dealing with that a little bit more. Somebody asked the question, which I think I sort of already talked about, was the Linac not available with dual spot and dual energy? I guess the answer to that is no. At the moment, you can have one switch. You can either switch energies or switch focal spots, and we chose to switch focal spots. So with the current availability, that was what we chose. Yeah. Okay, let's see what other questions are in there. Max part weight and height, again, 2 meters kind of cubed, 1,000 kilograms, 1,000 kilograms in weight. Somebody asked specifically, Tyler, about the 15,000 defect and what was kind of the dimensions of those components. About what, like 18 inches?
Yeah, I was going to say the part that we've scanned was around 18 to 20 inches in diameter that we scanned, and we're able to see a 15,000 defect. Do you monitor their MTF and CDF numbers to correlate what is a good scan for metrology? Yes. So we have different system performance checks that we do daily on the system. That we use ASTM E1695 to kind of monitor the performance of the system and kind of gauge if anything's going on. And we also do different type of detector and vocal spot checks to see if the system's properly functioning.
This is kind of a fun question. You guys are asking a lot of really good questions. There's a ton of them coming in, so thank you guys. There's one about the wall thickness of the bunker walls, and then kind of other additional shielding around the Linac specifically. So the bunker walls are kind of varying. They're actually varying densities. They're high density concrete, and depending on exactly where you are and kind of what the beam effects are at that point in time. So for instance, the primary wall is about 6 feet thick. So we basically use 3 foot square bricks of varying high density concrete, and the primary wall is 2 of them thick. So in, again, the sort of worst areas or the primary areas, you've got about 6 feet of the highest density concrete, and then kind of 3 feet in a lot of the other areas, but the density is kind of changing. And then shielding, yes, there's local shielding around a lot of the components, the Linac, the 450 kV source, the motors, et cetera. There's a lot of components inside the cabinet that we've specifically tried to protect from radiation damage. We get them all? Somebody is asking for some slides or the technical data. Yes, we can definitely get that out to you guys. I think we kind of captured them all. Most of the questions that are there, and if we missed any, it's because you guys sent us too many, and we lost them in our list. So I guess we'll kind of close it there. We will go through the list and see if there's any that we sort of left unanswered, and we'll get back to you. Feel free to reach out on LinkedIn or directly through our website, or as a follow-up to this webinar. Kind of hard to give the high-level overview kind of to capture all industries here, but we're excited about this technology. We're excited to go inspect some previously uninspectable parts and kind of help you guys on that journey. So thanks again kind of for joining us. Thanks for being patient. If you try to join the first time in December, feel free to reach out. Feel free to visit, the site here in Cincinnati if you want to see it or bring your parts yourself. We would love to have you guys. think that's
Yeah,
it.
thank you very much, Shana and Tyler. Thanks for your time. Thanks for taking all the questions through. So for all those who joined, thanks again for joining and hope you found the content of interest. We would very much appreciate if you please fill in the survey. We look forward definitely from hearing from you, from seeing you at our CSC in Cincinnati, as Shana mentioned. And well, having said so, many, many thanks and have a good remaining day.